this library offers functionalities that enable one to work with powerful, to work with matrices and arrays that are significantly large in size. So one of the benefits of Numpy is that it has embedded mathematical functions in it, which are used to perform most of the functions that we are going to go through today. So this is going to be a hands-on session, and I'd like to ask if any one of you has Numpy installed on their machines. That is, if you're familiar with Python, and if you're not, probably you can open Colab. I don't know if you're familiar with Colab as well, so that you can follow along in this tutorial. So in the chat section, could you please highlight your preference? Are we going to use Colab or Jupyter Notebook as I share my screen? Are you guys able to see my screen?
No, I cannot see your screen from my side.
What about now?
Yes, I can see from my side.
Okay, thank you. So here I'm just giving you an overview of Numpy. Numpy stands for Numerical Python, and it was developed by Travis Oliphant. The most stable release was released 11 days ago. Yeah, and so as I've said, it's a useful tool commonly used to perform mathematical operations on data sets in the form of arrays and matrices. So with that, I would like to start with the basic examples of Numpy, because this session has to last only 1 hour. So you can code along, and in case you have any questions, feel free to ask them. So I'll start by showing you the basic structure of an array. So here I'm defining a simple array. And yeah, that's it. That's what an array is, and we can obtain a number of things about this particular array, such as the type of it. You can call it type A, for example. Okay, sorry. Just start by importing Numpy. Forgot that. Yeah, so you can see it's an array, and basically an array is a collection of that's been stored in some sort of a matrix. So what I can say is that the same way we have matrices of different dimensions, you also have arrays of different dimensions. By calling the function dim, is called as a.undim. Yeah, so we have an array of dimension 1. We can have other dimensions as well. Show an example. So this is going to be a 2D array, and we're going to see that by calling that. Okay, all right, this is a one-dimensional array as well. Sorry for that. Okay. And just a concern, I'm not sure if we are together with everyone. This is going to be difficult to follow through. So I don't know how I'm going to know if any one of you is stuck. Would you please respond at the chat section? Hello.
Hello. I think if they are not getting, they can reply to the chat, or somebody can just unmute and say that you have left us behind. Yeah, I think that will be better.
Okay, fine. These first two examples are just showing the basics of arrays. That is, one of the biggest challenges that you may have to face is to extract information from the arrays using by indexing various values of the array. So the first thing that I want to show you is how you can index a specific value of an array. So let's do it. So in Python, we don't start numbering things from 1 conventionally. We start from 0. So if you want to access the first element of an array, you're most likely going to start from you're going to start reading it from index 0 rather than index 1. So for example, in our array A over here, if you want to access element 1 over here, you're going to call it as a 0. So you can say that the first element will be A0. So if you call that, we're going to have a 1 over here. So in the event that you have an array with, let's say the dimension of your array is greater than 1, you will have to pass in the row and the column of the element that you wish to identify. So, and that's what I'm going to do here. So given this multidimensional array, if I want to get the first element in this array, I'm going to pass in the row value, which is 0, and the column value, which is 0. Passing this is going to return element 1, as you've seen. Okay. The next thing that I'd like to show you is creating arrays or matrices that are populated by a specific number. For example, you may want to create a matrix, a 3x3 matrix, for example, that is only made up of zeros. So Numpy provides you with a function doing that. So you can say that zeros is equals to numpy.array 33. So yeah, this is the output that we get. But if you want to see them in an array format, let's see. Can now do so this is the 3x3 matrix that I've been telling you about. So it's a 3x3 matrix that is composed of zeros only. You can change this value to your own custom defined value. For example, you could work with ones, for instance, and you could change the dimension. Maybe if you want a 4x4 matrix, that is what you get. So apart from zeros and ones, you can also give in any value, like any value that you want. Maybe let's say you want a value, an array of value 101. So that can be obtained by doing the following. So let's say you want a 2x2 matrix filled by 101s. So if you call that, sorry for that, missing a comma here. That's what you're going to get. So basically, this is the structure of an array, which forms the basic data type that most Numpy operations are based on. of performing complex mathematical equations. And one of the examples of an equation that can be performed using Numpy solving simultaneous equations, that is linear algebra. So the next example that I'm going to show you is how Numpy can be used to solve an algebraic equation. So, okay, let me just do this. Just a moment, I'm fetching a question somewhere. Okay, so this is a common equation that most of us may have interacted with. So consider an equation given by that. If you want to solve it, you can translate this equation into a matrix, and this is the solution of that matrix. So we know that to solve any given set of simultaneous equations using the matrix method, you first multiply the inverse of the original matrix by the solution of our simultaneous equations to find our unknowns. So here I'm going to show you how this can be done using Numpy. Okay, so we are going to start to define our array first. So I'm also going to define our solutions. Let me call them the solution, just avoid confusion. So the first step, as we've said, is to find the inverse of the matrix. So you do that by saying A inverse is equals to Numpy dot A, and I think we can see that's the inverse of our matrix. So find the solution, which are the unknowns. We now get the dot product of the inverse of this matrix and the solution to the simultaneous equations that were provided with. So that can be obtained by doing np dot the inverse of the matrix and the solutions. So I'm just forgetting something here. Let's call these unknowns. So we find that our unknowns are 5, 3, and minus 2. So if you try and solve this equation using your hand or any other software that you're comfortable with, you find that the values of x, y, and z are 5, 3, and minus 2, respectively. Okay, so I don't know if there are any comments on the chat section. Okay, Victor is saying that she can't hear anything. I'm not sure about now. Hello, is there any feedback at the chat section that you would like me to address?
Yeah, somebody is saying you are moving a bit fast.
Okay, is it possible that you tell me where I went too fast so that I could repeat? Hello? Okay, fine. Let me look at line 13. Okay, so here at cell 13, I was showing you how it's possible to create a matrix or an array with your own predefined values. So this example that I was providing here is creating a 2x2 array that is populated with the value 101. So the 2x2 dimensions have been declared over here, and the 101 values that are going to populate the array is what I have over here. I'm not sure if that's clear or if it has answered your question, Serafina. Okay, you're welcome.
She said thank
any
you.
other concern? Okay, so we are going to proceed. So apart from arrays, as I said when I was beginning, Numpy contains a number of inbuilt mathematical functions that can be used to solve various problems. So in this next section, I'm going to show you all the mathematical functions and the statistical functions that are inbuilt in Numpy. So in this next section, I'm not going to work with arrays, rather you're going to work with lists because they're much simpler to work with. So I'm going to declare a number of random numbers that I'm just going to choose at random. So we say that I have this. So using Numpy, we can find things like the mean of this selection of numbers, the standard deviation, the maximum, the minimum, and things like those. So the list is endless, but I'm just going to highlight some of the most used functions. So if you want to find the mean of this selection of this list, for instance, in unknown numbers, if you want the standard deviation, it can be obtained by passing the std function, the numbers. The minimum can be found by just passing the mean argument. And finally, the maximum can be obtained by passing the max argument and giving the numbers to the input. So the mean of these 5 numbers is 13,457. That's the standard deviation, is the minimum value, and that's the maximum value. So that's the basic statistics. Let me just show you over here. So the basic statistics. So if you want to do some basic operations, like the addition, subtraction, multiplication, maybe division, they can also be done by using the inbuilt functions that are provided by Numpy. So I'm going to show you how to do some basic addition, subtraction, and multiplication. So if you have 2 variables, say variable 1 is 30, and variable 2 is 50, you can find their sum by doing numpy.add var1 var2. Okay, the difference can be found by numpy.subtract var1 var2, and their product can be found by passing the numpy.multiply argument and passing the variable 1 and variable 2. So we can print each of our results as follows. So if you add 30 to 50, you get 80, and the difference is -20, and the product is 1500. Again, these are just basic operations. You may want to do more complex operations, or the operations may be performed at a larger set of numbers rather than just these two variables. So since this is an introductory session, I just thought it necessary to show you these basic fundamentals. So again, any concern from the audience or something like that? Question? Okay, so I'm going to go ahead to the next part of this presentation. I want to show you a more practical example of how you can apply Numpy in performing linear regression. So if anyone of you has any experience with or has interacted with statistics, you've probably heard of linear regression. So there's a linear relationship between a given set of dependent variable and independent variables. So it can be used for regression analysis and such problems. Python has a library called sklearn, which comes with a package for performing linear regression, so you really don't need to add code the entire process yourself. However, I'm going to show you how the same process can be done using Numpy, so that at least I may illustrate the different inbuilt functionalities that I've been talking about in the previous sections. So feel free to bring them up. Just a disclaimer, this is going to make use of object-oriented programming. So if you don't have any experience with that, again, don't feel, don't be afraid. You may take your time and go through it later on. Okay, so I'm going to start to implement the linear regression model. So this model is going to take in things like the arguments like the learning rate, the number of iterations that are going to be performed in the regression. So I'm going to put that in 0.00. So I'm going to declare each of these here as follows. So the learning rate is equals to self.number of iterations So just before I go on, I'd like to show you some basic theory behind linear regression. So as I've said, it's a statistical approach that assumes there's a linear relationship between the independent variable and the dependent variable. So the fundamental equation behind linear regression is given by y is equals to wx of the features x, that is, and then b is the bias in the model. So using this, we are able to perform predictions on features and try and predict their variables without knowing them explicitly. So I think this forms the basis of machine learning or data science. I mean machine learning. So what I'm going to implement here is how this equation can be performed for a given number of features, say 1,000, using Numpy. And the primary objective is to show you the inbuilt Numpy functionalities that are used to implement the linear regression model in Python. Okay. So the next process will be to create a fit function here. x in x and y. So one of the things that I'm going to declare are the number of samples and the number of features that are going to be fed into the model. So essentially each feature has its own weight. So that's why I'm declaring that the initial weights are going to be 0, and they are going to be of the size of the features that we are going to feed into this model. I'm going to iterate through this number of iterations and fit in this model over here. And for every iteration, we are going to update our weights and our bias so that this model might be able to learn more effectively, so that it can perform the regression or classification task that we are going to pass in much later on. So these are going to do that. I'm going to say that that in range number of iterations I'm going to say that our predictions are going to be given by the dot product of our features and the weights plus b. So here, essentially, what you are doing, we are implementing this step here, which should say that the y is given by yx plus b. So as I told you earlier, b bias and w is the weights, and that's what we've done over here. So having done that, we may want to obtain the gradients of our weights and our biases so that they can be used to update these values over here. So to obtain the gradient, I'm going to do the following. So the dw will be given by, dw is the gradient of the weights, given by n, 1 over n samples, multiplied by the dot product of the transpose of our features and the difference between our predictions and the actual values. So that will be times dot t, and then take h minus y. So that's the formula for calculating the gradient of the weights. And the gradient for the bias is going to take in the of the x features. So the bias will be calculated as db is equals to 1 over n samples times input sum minus y. So I want to believe this is correct. Okay, so once we have the gradients, we are going to weights equals to self. We're going to multiply the learning rate times the gradient of the weights and the self dot bias is to self dot learning rate times the dB. Okay, so that's it. So essentially what you're doing here, I'm going to repeat once again, is that for every iteration here, we are creating a predicted value of y by taking the dot product of the features and the weights plus the bias. So this, the y is equals to wx plus b equation over here. And then to obtain the gradient of the weights, we're taking the inverse of the samples and we're multiplying it by the dot product of the transpose of x and the difference between the prediction way, but this time we are not considering the transpose of the features, but rather we are only considering the difference between the predictions and and the dependent variable, which is our y. So once we have these gradients, we update our weights and our bias, which initially had been set to zeros. So this process is what is commonly known as gradient descent. Okay, so once we've done that, the next, so we're going to call this thing called predict. It's going to take so what the predict does, it's going to use what we've defined here to make new predictions. So I'm just going to do equals to dot. And once you have the predictions, we want to return them. So we are going to return our predictions. Then the next step will be to evaluate how our model has performed. Okay, so just in case anyone has a question regarding how this mathematics has been implemented here, you can feel free to ask. Any question? Hello, Joseph. Do you have a question? Okay, fine. I'm going to.
Yes, I was asking if you can.
So
yeah.
Okay, so as I said, I'm going to start from the basic definition of linear regression. So it's a statistical approach that is used to find the relationship between a dependent variable and independent variable or variables, depending on the number of variables that we have. So a common example of a regression problem might be we want to predict the house prices in a given area. So our dependent variable will be the price of the house. Our independent variables will be the number of features that determine the price of the house. So you can say that maybe the price of a house in a given region depends on things like the neighborhood and things like those. Okay, so given that information, we can come up with this relationship here. Say that y is equals to wx plus b, where y is the price of the house, x is the features, w is the weight of each of these features. We know that some features may have more weight when it comes to determining the price of a house compared to others. And b is the bias that we're going to feed into this model of scenarios or samples. Maybe you want to predict the house price of 1,000 houses or so. We are going to do this through iterations. So when implementing this, the first thing you are going to pass in is the learning rate. Learning rate, basically what it does, it determines how quickly our model is going to learn the patterns that are going to determine the price of the house. So one thing you need to know about a learning rate is that if you select a high learning rate, this model is going to hastily go through the data and it might miss out important points. On the other hand, if you select a very low learning rate, yes, the model might perform well, but it will take an extremely long period of time. So you have to be very careful when selecting a learning rate. The number of iterations, as I've said, is the number of times you want our model to run through the given samples to come up with these predictions. Again, you need to be careful when selecting this number of iterations, because if you select a few iterations, the model won't run enough times to come up with proper predictions. Okay, so this is what I've done here by establishing the learning rate and the number of iterations. The weights, as I've said, these are the value we attach to the different features in our model that are going to determine the dependent variable. The bias is the one that ensures that our model does not overfit and things like so. So to begin with, we are going to put our weights as zeros. So this is one of the primary applications of Numpy, zero weights that are the size of our features. So for every feature, initially we're starting with 0 weights. The bias is 0. So for every iteration, our primary objective is to update our weights and our bias, but first as 0 plus the self-weight bias. Essentially, that's the primary equation of the linear regression model. So once we have in our biases, and to do that, we need to find their gradients. So this is how we compute the gradients. Unfortunately, I don't have a marker pen or something which I could use to simplify this, but maybe after this presentation, I can share with you a reference notebook and a reference link that you can use to find more information on updating our weights and biases based on their gradients. So once we've found this gradient for all these iterations, we are going to update our weights using this formula. If you see here, if you look keenly, you'll see that we are considering the negative direction, because when you are computing the error, you want your error to be as low as possible. So we are trying to approach 0. So that's why you're putting here a negative, a negative. Okay. So the weights and biases are reducing so that our error can be as close to 0 as possible. So once we have these weights and biases, finally, after 1,000 iterations, that is, we now come and predict our predictions. We now come and obtain our predictions using this formula over here. Essentially, this formula is the same as this, but now instead of using the initial weights and biases, we are using what was updated over here. And then finally, we return this prediction. So I don't know up to that point if I'm clear. Okay, thank you. So, can I proceed? Okay, let me proceed. So here, I want to make that will help us gauge how this model has performed. So essentially what I'm trying to say is we need to come up with an error metric, since this is a regression problem, and in regression you mainly focus on the error. So I'm going to call a function called the mean squared error that is going to take in our predictions and the actual value. And what this function does, it's going to return an error score of these two. So it's going to be, this error score is going to be given by the mean of the square of the difference between the actual value and the predicted value. So it's going to be the mean of the actual value minus predicted value minus predictions. But as you said, it has to be squared. So I'm going to square that. Okay. So that's it. So we have our model over here, the linear regression model over here, and the scoring function over here. So what's left, we are going to create a dummy set of data that's going to evaluate how this linear regression model has worked. So I'm just going to do that quickly because of time. You don't have to worry much about this. This comes installed with Python for those of you who have experience with it. So we are making a regression data set that contains 1,000 samples, and we only have one feature. So yeah. So this is our train set, test set for the features and for the targets. So once we've done that, and now call in our model, say that the regression model okay, then I'm going to call in the fit function. We are fitting it in our training set first. And then for the predictions, we're going to obtain them from the test set. And then finally find our score, rather the error score. We're going to call in the mean squared error. We'll pass in the predictions, the y-test. So finally, you can see what the score is. Train. So you can see that we have an error of 445.16 based on the model that we've created. This shouldn't be the concern. What I wanted to pass across is how the different inbuilt functionalities of Numpy can be used to implement the linear regression model. So as you've seen, we've used the np.zeros function that I'd spoken about. Then we've also used the dot product function over here, the sum, and finally the mean. So yeah, that's it, unless anyone has a question. Is there anyone with a question? Okay, fine. So I'm just going to share with you the link to. Okay, Julius.
Yeah. Hi, Patrick. So my question is, you said that we be very careful while determining the LR and N iterations. Okay, finding we make sure that we have a number that maybe covers that will give that is optimum. So like, what is the rationale behind determining that number, or how did you come up with 1,000? Why not 15?
You just make an educated guess, because if you take a number, a big number of iterations, maybe if you say 10,000 or 100,000, while it may work for you, the computational resources involved might be significant. Okay, so it may take a very long time for your model to train. The same applies for the learning rate over here. If you put a very low learning rate, your model is going to take a very long time to train, and probably there might be no significant improvement in the performance. So yeah.
Okay. Thank you.
Okay. Any other question? So I've just shared a notebook that contains what we've been doing this evening. So if you may want to go through it later, more slowly, there it is. So I think if there's no other question, then I want to thank you all for taking part in this discussion. Oh, you're asking for practice questions. Yes, I can design some and then share with you later on. You're welcome, Tebogo.
So can I take the session, or you are still waiting for some more questions?
No, I don't think there are any questions, but if they are, they're free to ask.
Okay. Anyone with any question?
The access has been denied access to what you shared.
Please try out this new link and see if it works.
Yeah, it works. Thank you.
You're welcome.
Thank you, Patrick, for the session, and also thank you to all who came and attended the session and took part. Yeah, so I think that will mark the end of Numpy sessions. In case we have any, I think it will be a more practical session with a given data set. And to answer Adam's questions, yes, you'll get the recorded session. I will upload it to our YouTube channel. Yeah, so I would like to say that tomorrow we're going to have 2 sessions. One is going to be a soft skill session, and the other one is going to be the normal R weekends. So I humbly implore all of you to attend the session. And since we have been lagging behind, I think we have had too much theory and too much collab sharing of notebooks. It's time we start doing projects, and yeah, we start kuchuja watu from the boot camp. Yeah, those who will not be doing the projects. As for the Git assignments, I have received them, and I wish to tell you guys to prepare for the next project, which will be coming next week. Yeah, if you have any question and inquiry, kindly feel free to ask. And the form I have sent, yeah, kindly make sure you have signed it, because once it reaches 9 p.m., I'm closing the form. Thank you. Anyone with a question? No one. Awesome. Thank you. Good night. Oh, the YouTube channel name, it's Data Science East Africa. Which form? Let me share in a few. Yeah, that form. Yeah, if anyone wants any help or talk to Patrick, yeah, just let me know. Thank you.
Thank you.
Olayami, sorry for that.
Yeah, Patrick, thank you very much for the lesson. I will go through the recording because I still.
Pardon, I can't get you clearly.
Okay, I said I will go through the recording, but I joined late, so that I can get the full understanding of what.
Okay, please send a chat because because I can't hear you completely. Anyone else with a question or a concern?
I have a compliment. Nice presentation and composture. Yeah.
Thank you. Thank you very much. Okay, so thank you all for attending. I think, yeah, Olaye, I've just seen your message. Yeah, your questions are welcome. If you have any, feel free to reach out. Okay, so I think that's all from me. I'd like to wish you all a great evening, and for those of you who are on a different time zone, have a pleasant day or night. Thank you.